Okay, so the first talk is by J.T. Schindler about X-ray shooter and ALMA sample of quasars in the Epoch reionization. J.T., go ahead.
Yeah, hi everyone. I'm currently a postdoc at the Max Planck Institute for Astronomy, and I want to start out by thanking the organizers for giving me the opportunity to present this current work in this setting. So I would like to introduce to you the X-SHOOTER ALMA sample of quasars in the epoch of reionization. So when we investigate high redshift quasars, there are multiple questions that we ask ourselves that we want to investigate. And I want to highlight two of them. The first one, how do the first supermassive black holes form and grow? And we try to address this question by measuring black hole masses, adding to luminosity ratios, quasar lifetimes, and the quasar luminosity function. The second question that I want to highlight is, how does feedback shape the onset of galaxy supermassive black hole coevolution? And to answer this question, we need information on the galaxy host, like the galaxy stellar mass, star formation rate, gas mass, or information on quasar winds. So part of this information we get from the rest frame UV spectrum of the quasar itself. It allows us to investigate the accretion disk, broad emission line regions, intervening absorbers, and the intergalactic medium. Today, I would like to focus on the first two, which give us information on the black hole masses via single epoch viral estimators, as well as on the line components and the line velocity shifts. We then combine this information with information from the galaxy host, which it can be famously provided by ALMA by investigating the C2 150 micron transition. And here are some resolved observations of one of the quasar hosts. So whether the observations are unresolved or resolved, they give us information on the galaxy host, like the star formation rate, dynamical gas mass estimates, and so on. So with the sample that I'm presenting today, we'd like to combine this. Our sample consists of 36 luminous reionization era quasars with ALMA literature data and newly produced X-SHOOTER spectroscopy, which we have analyzed within the last year, with our goal in mind to investigate the quasar and its host both. Here's an overview of our sample and the bolometric luminosity redshift plane with our objects highlighted in solid orange. All of the quasars in this plot have near-infrared spectroscopy data. I would like to emphasize one of the largest samples, which is from Shen et al. At redshift 6 or so, extending also to lower luminosities. So we get information from the carbon-4 and magnesium-2 lines by fitting them in the near-infrared spectrum, as well as the iron continuum. On the right, you can see an example fit of one of our spectra. This allows us to derive black hole mass estimates, to measure the iron 2 of magnesium-2 flux ratio, which indicates broadline region enrichment, or it allows us to look into carbon-4 to magnesium-2 velocity shifts, an indicator for winds and outflows. And then we combine this information with the ALMA data. In this case, I would like to show you the information on the broad emission line velocity shifts with respect to the carbon to redshift, but other projects in the works, such as supermassive black hole galaxy coevolution. So let's dive right in. So at first, I'd like to show you the black hole masses. So here's the bolometric luminosity black hole mass plane with our sample again highlighted in solid orange points. So these black hole masses span a range of a few times 10 to the 8 to up to 10 to the 10 solar masses with a few outliers up here. So these have Eddington luminosity ratios between 0.14 to 1.46, which indicates high accretion rates. So these results reinforce the picture in which massive and highly accreting supermassive black holes are already in place in the epoch of reionization, putting strong constraints on the formation models and early growth of supermassive black holes. Furthermore, I would like to draw your attention to the iron enrichment in high redshift quasars. We try to constrain this with the iron 2 of a magnesium-2 flux ratio, which is a proxy for the iron of magnesium abundance ratio. Since the iron and magnesium is polluted into the ISM with a time delay of about 0.2 to 0.8 gigayears, depending on the stellar and binary evolution processes, we would expect that nascent galaxies experiencing the first burst of star formation would be first enriched in magnesium-2 before they are enriched in iron. So the flux ratio, which I'm showing on this axis, is expected to drop at the very highest redshifts. However, we don't see this trend in the combined sample of ours. And in fact, if we look at the median ratio, it seems to be pretty constant over time. So we conclude that quasars at redshift 5.8 to 7.5 have already iron-enriched broadline regions, suggesting a rapid iron enrichment in the first 0.8 gigayears. And here I would like to draw your attention to this highest redshift data point recently published by Masafusa Onu et al. From here, we move on to the carbon-4 to magnesium-2 velocity shifts. This velocity shift is seen here on the y-axis against the magnesium-2 redshift. A recent paper from last year showed the mean velocity shifts to strongly decrease at the highest redshift. So we see very large blue shifts in the carbon-4 line. Our sample also is shown in orange here, and if we bin our sample to the same bins as the Meyer et al. Data, we find extremely good agreement. This is owed to the fact that our samples overlap quite a bit. However, it shows the consistency of our different methods. So large carbon-4 velocity blue shifts seem to be common in these high redshift quasars. And we find a median of about minus 1,800 kilometers per second. So this suggests that there is a radiation-driven outflowing wind present in many of these objects. If we compare our quasars to a low redshift luminosity matched sample from SDSS, as shown in the gray histogram here, we can see two things. First, the median is strongly different. And secondly, even though the median is very different, we find large carbon-4 blue shifts even in the low redshift sample, leading us to conclude that low redshift analogs in bolometric and carbon-4 blue shift to these quasars do exist. At last, I would like to compare our sample with the recently published Shen et al. Sample from last year, which find a discrepant carbon-4 blue shift of minus 330 kilometers per second. We've started to look into this, and it seems that part of the reason is difference in the measurement methods. So with regards to these large carbon-4 blue shifts seen in these high redshift objects, it is still unclear whether this is a selection effect or actually a change in the broadline region conditions. So we need to further investigate this. So now I would like to come to the synergy with the ALMA data. And here I'm showing you the carbon-2 emission line compared to the broad emission lines from the quasar X-SHOOTER near our spectrum. You can see how narrow the carbon-2 line is, showing you that it gives us a very precise systemic redshift estimate. So we now exploit this information by looking into the magnesium-2 to carbon-4 carbon-2 blue shift, excuse me. And so here's our sample, and we see, or we find, a moderately blue shifted magnesium-2 line compared to carbon-2, with a median velocity of minus 390 kilometers per second. So this has already been seen in some smaller samples, as well as in lower redshift samples. So we did not stop there, but we looked at correlations between these magnesium-2 velocity shift and the carbon-4 velocity shift, both with respect to the host galaxy's carbon-2. And we found a significant correlation, which indicates that there is a common physical origin for these blue shifts. We did not find any correlation with the adduct-to-luminosity ratio, which you might think of at first. So with that, I'd like to conclude and summarize. So I've presented to you the X-SHOOTER ALMA sample, which is comprised of 36 luminous reionization era quasars, which are based on ALMA literature data and newly homogeneously reduced and analyzed X-SHOOTER NIR spectroscopy. Our goal is to get a comprehensive view on the quasar and its host galaxy, so the whole quasar phenomenon. Here are the results that I presented today, but this is only the start. So please stay tuned for more results coming in the future months. Thank you.
All right, thanks, JT. Questions on the Slack? Anybody any questions? Okay, while you're still typing, let me ask one first. You showed that the iron-MgII ratio is a constant, and are you really predicting when we find redshift 10 quasars, this trend is going to go down?
So this is a bit more complicated. There is the assumption that the iron 2 of magnesium 2 flux is a good proxy for iron over magnesium. But it has been shown in some studies that there's actually a density dependence on these emission lines. So it is a more complicated picture than I've painted here in these few minutes. If this assumption holds, then we should expect this to go down. So there are some works by Samishima et al. 2017, which show some theoretical predictions of this.
All right, thanks. Other questions? Okay, so Brent Robertson asked, given the matter enrichment, can you say anything about the relative growth of the black hole and stellar components of these objects in early times?
I don't think from that information we can draw any conclusions about this, because the predicted delay times are not very certain. But I believe, so we're working on basically putting the star formation rates and black hole accretion rates in comparison for all of these quasars, as well as their the galaxy dynamical masses and the black hole masses. So we should be able to say something about their coevolution with that.